morning. How are you guys doing?
Awake.
It's Monday morning. Why do we have Mondays? I think it's time. Yep, it's 9 o'clock. I'm gonna get started here, and let's see, turn on the mic here. Yep, that's good. If not for anything else, it allows me to kind of walk around, and then the microphone will still be recording at the same level. In some of my other classes, I would walk around, and then the volume would change depending on how far I got from the mic. So with this class, it's not going to be as much of an issue. So I'm not really sure how much of the material you guys have time to read. And you were supposed to read ahead of me a little bit. Okay, so a few things. First of all, I found out whether tuples are supposed to nest or not. In other words, okay, let me get back to basic set theory. It is the last part of this that I raised a question in the previous class of what if you have two Cartesian products applied in sequence. Would it produce tuples that are nested or not? So that's the question. So we covered all the material up to this part here from the previous lecture. So what I did was I looked up whether Cartesian products can nest or not, and if they do, how do they nest? Okay, when we have consecutive Cartesian product operators, what do we end up with? So here's the answer. I looked up on the web. And found this to be the answer, and I kind of verified that too. I'm not just reading off of a website and okay, that has to be the answer. So here's the answer. Here's an example. So the example has, in this case, we have 3 different sets, and we have 2 Cartesian product operators. So the question is, what is the end result of the application of the Cartesian product in this particular case? So as it turns out, this is the same thing as this one here. You can see the only difference is I put parentheses around the first application of the Cartesian product. It is also considered exactly the same as the third form, where I put parentheses around the second Cartesian product. In other words, it operates just like addition and multiplication, where it's associative. So how you put the parentheses does not really change the meaning of the operation. Is that okay? All right. But that also means that when you look at tuples, not the Cartesian product, but the result of the Cartesian products, this has to hold true as well. In other words, if you have a 2-tuple, which is where the first item is a 2-tuple itself, it is the same thing as a 3-tuple, where you have a tuple with 3 items inside, and there's no structure, no nesting whatsoever. And you can also restructure it so that you have one single item, and then you have a second item that is a 2-tuple, and all 3 are considered equivalent, at least in the context of this class. Are we okay with that? All right. So the last part here is basically saying sometimes if you look at a quote-unquote flat tuple where there's no structure, there are no additional parentheses inside, you can impose a structure and it will still be considered the same. So in this case, I have a flat tuple, a flat 3-tuple, because there are 3 items in a tuple, 1ax. It is actually considered the same thing as a 2-tuple where the first item is 1a and then the second item is all by itself x. Is that okay? All right, so bottom line is you can add parentheses any way you want, as long as the ordering of the individual items does not change, it will still be okay. Now this comes in very handy, very useful later on when we start to talk about functions. Because when we talk about functions, that's when tuples become really, really helpful, because we need to associate one thing with another thing. Okay? Set theory by itself cannot do that. So when we introduce the concept of functions, then we can start to say, oh, we are mapping this thing to that value over there. And that's when tuples become extremely useful. So So that's that. So I answered the question that I asked myself in the previous class. How many people did the self-assessment? Was it helpful? Do you guys have any questions about the self-assessment? Yes?
I had a question on the last one.
On the last one? Last question?
Yeah.
Okay, let me take a quick look here. So last question, number 6. I'm not sure whether they're ordered exactly the same way or not. Is this the last question?
Yeah.
Okay. So the question is asking, given two particular sets, U and V, what is the union of V minus U and V intersecting with U? Okay, so there are several ways to look at this. You can look at it using an example. Okay, define a particular set U and a particular set V where they do intersect, and then you can just figure it out. Okay, you can also look at the Venn diagram and look at the picture and see how that might work out. Okay, so what I'll do is I'm going to switch to my document camera here and just draw a picture of that particular question. So we have a set U, we have another set V, they have a little bit of intersection. And let me read the question again. So we are looking for V minus U and then the whole thing union with V intersecting with U. Okay, I'm switching back to the camera now. Okay, so what you want to do is to figure out each term individually. V minus U is asking what is in V but not in U. Okay, so what is in V but not in U is this portion. We are excluding the intersection, right? And then the second one is V intersecting with U, and that's basically asking what is in both sets. And that's going to be this part here. The union is saying, okay, if it's in either one, either V minus U or V intersecting with U, then it's in the result. And you can see that you just get back what?
V.
Yep. Is that okay?
Yeah, that makes sense.
Okay. Yeah, sometimes pictures really help,
I was trying to figure how the Venn diagram would be, but I didn't know if it'd include the intersection because that includes U as well.
Oh, okay. So it's not going to include U because that's the whole purpose of the quote-unquote subtraction, which is called a difference operator. And basically what it's trying to find out is what is in V but not in U. Okay, so that's good. The quiz or the self-assessment is working. Any other questions about the self-assessment? No questions? Okay, all right. If there are no questions, we're going to move on to finish up, set theory today, hopefully. Well, maybe we'll do that. Okay, the next topic is the concept of a power set. Now, this is an interesting concept. It can be very confusing as well. So we'll start with the definition of what a power set is. The power set of a set S, in this case, is the set of all subsets of S. Okay, so instead of just looking at the definition and saying, yes, I know what each individual word means, okay, let's see if we can kind of tie everything together. The first thing that we need to understand is, what do we mean by subsets of a particular set? Okay, that's the first question. So the best way to do that is to use an illustration on a piece of paper. Okay, so let's say the set that we are dealing with is, has 3 elements, 1, 2, 3. Okay, so this is the set that we are considering. So now I'm asking you the question, what are the subsets of this particular set? In other words, what kind of set contains elements that are also in this particular set, but only from this particular set? All right, so in this case, the empty set is a subset of 1, 2, and 3. By definition, the subset is a subset, excuse me, the empty set is a subset of any set, including the empty set itself. But we can also have a set of just, 1, okay, because in this case, this set has exactly one element which is also in the original set. Okay? 1, 2, 3. These sets are all individual subsets of 1, 2, 3 as a set. Is that okay? So now we can start to look at, what about 1, 2 as a set? Is that a subset of 1, 2, 3? Sure. What about 1, 3? Yep. And then there's also 2, 3. So these three are subsets that have two elements, but they are also subsets of 1, 2, and 3, because all the elements of these individual sets can be found in the original set. Okay, so what about the last one, which is 1, 2, 3 itself? Is it a subset of itself?
Yeah.
Sure.
Yes, it is. Okay, because 1, 2, 3 has all the elements from the original set, and only from the original set. But tag is exactly the same thing as the original set. Yes.
That's the one with the underline.
That's the one with the underline. Very good. So it's kind of like a subset or equal to. Yep. But it's also called just a subset. Now, 1, 2, 3 is not a proper subset of 1, 2, 3, which is the one without the underline. So it's kind of like the same thing as a less than. Okay? So how many subsets do we get here? You can just do the counting real quick. There are 8 of them. Okay? So how does 3 relate to 8?
Base 2.
Base 2 and
Exponent.
2 to the power of 3 is 8. In other words, if the original set has n items, then it has 2 to the power of n subsets. Is that making any sense? Sort of? Because something can be either in or not in the set, and all the subsets are independent. So that's why that equation works. Alright, so getting back to here, I use my own example, where the cars that I like, consist of the Miata, the MR2, and the Civic. So the power set would be the empty set. You guys get the idea. It's the same thing as the example. Okay. And the notation of power set looks like a funny P symbol here. And in this case, I basically repeated. I'm just repeating myself here. If a particular set has n elements, then the power set has 2 to the power of n subsets, or 2 to the power of n elements. Is that okay or not? All right. Now we do have practical applications of the power set, and we have been using this and not really quite realizing that we have been using this. Think about binary numbers. Okay, so what are binary numbers? What makes binary numbers special and make it different from any other basis? Each digit can be 1 or 0. Okay, very good. So when you look at something and whether it belongs to a particular set or not, do you see a parallel between what can be in a digit of a binary number as opposed to whether a thing can be in a set or not? Do you see the parallel? Okay. It's base 2 or binary. Okay, you only get 2 choices. Okay, I'm just gonna write it down here, so it's gonna be recorded. Here we go. So when you look at a binary number, let's say 1, 0, 1, 1, you focus on one single digit, and you say, okay, that digit can either be a 1 or a 0. Okay, you got 2 choices. Is that okay? And then you look at items that can be in the set. Okay, so I'm gonna put the 740 back here, the Miata. This case, we'll throw in something else, CRV and the MR2. Okay, so these are individual things. Whether they belong to a particular set or not, is not clear in this picture. Is that okay? So in the case of the cars that I like, the 740 is not in that set. The Miata is in that set. CRV is not in the set. MR2 is in that set. So in other words, I end up with a set that only has Miata, and MR2. But do you see any parallelism here between a digit from a binary number and a thing that can be in a set? 0 and 1 versus it's in or not in a set. Is that okay? All right. So the next thing I want to do is to say, well, in that case, can I express a binary number in a slightly different way as a set? Okay, so let's take a look at a binary number. Let's take a look at an 8-bit binary number. 0, 1, 1, 0, 1, 1, 0, 1. Okay, for no particular reason, I'm just using this as a binary number. So this is a fairly typical way to represent a binary number, which is, the least significant digit is on the right-hand side, the most significant digit is on the left-hand side, and in each place, okay, the position of the 0 and 1 implies, which quantity is indicating, right? So I'm now saying, hey, I can just represent this number as follows. Okay, so I will just write down the alternative way to represent a binary number, and you guys can tell me how that works. And I'll try to throw in as much confusion as possible here. So we put a 2, 6, 0, 5, and I'm missing 1 here. I think it's a 3. There we go. Okay. So I claim there is a way to interpret the set to mean exactly the same binary number. How? What are those numbers corresponding to in the set? Yep.
The power of 2 that it represents.
The ones, right?
Yeah.
Very good. Okay, so you're observing that I'm
First one's 2 to
representing.
the 0, one's 2 to the 1, 2 to the 3.
Exactly. So that's one way to represent a binary number as a set. Okay, so the concept of a binary number and the concept of a set, they're actually closely related, because a lot of times in terms of implementation, we actually use binary numbers to represent sets. Is that making any sense?
Okay.
Sort of? Okay.
Why do we have a different number of digits in the set?
So that's why it only works for binary numbers. This is where you can actually visually see the relationship, special relationship between a binary number as opposed to a set. It doesn't work with base 3, because in the base 3 number, each digit can be a 0, a 1, or a 2. So it doesn't fit well in a set representation anymore, because in this case, the set representation is just saying, okay, give me all the powers of 2 that has a 1 corresponding to that digit. Okay, so there's okay, let me draw the links here. There is 1 to the power 0, there's 1 to the power of 2, 1 to the power of 3, 1 to the power of 5, and 1 to the power of 6. That's how these two representations relate to each other.
So is this an unordered set?
They are always unordered. Every set is not ordered. When it's ordered, it is not a set anymore. It becomes a tuple. So the ordering of a tuple is important, but the ordering within a set is not important. That's what I said. That's why I said try to throw in as much confusion as possible, because I intentionally did not list the numbers as 0, 2, 3, 5, 6, because that would make it too obvious. I intentionally kind of throw the numbers all over the place just so that you guys can see, hey, the ordering does not even matter. Okay, if the value is in the set, it is in the set. It doesn't really matter how I list the elements in a set. Is that good? Any questions about this picture? No questions? Okay. So when do you think there is a necessity to represent a set in an algorithm? Never. Yeah, this is all theoretical stuff that will never be used in real life. Companies like Google, Facebook, will never really care whether you understand set theory or not. If that were the case, I would not teach this class. even if it's assigned to me. Because I refuse to teach anything that is totally useless, at work. So, if that is the case, can someone name an algorithm where the representation of a set is actually important? Now, it's okay if you cannot name an algorithm because you may not have taken enough classes to understand that, oh, okay, there are these algorithms that rely on the representation of sets. Yep, go ahead.
One, I think A asterisk.
A star?
Yeah, A
Yep,
star.
very good. Okay, somebody actually, when did you encounter the A star algorithm? Because I haven't taught it yet in this class.
Just my own research for a long,
Your own research?
long while ago.
I think Iraj touched on the Dijkstra's algorithm, which is a simplified version of the A star algorithm. So I'm just gonna throw that in here because we are going to revisit the Dijkstra's algorithm and A star algorithm. But I'm just gonna throw it in here, Dijkstr. Okay, so this is called Dijkstra's algorithm, and Dijkstra is a Dutch computer scientist who is also considered one of the important modern computer scientists. He's not quite at the same level as Turing in terms of as the father of computer science, but he has a lot of contribution as well. So our job here is not to go through the entire thing, but what we're going to do is to go take a look at the algorithm. So description, pseudocode, right there. And this one does not make use of a set, unfortunately. Okay. Let me look for A star algorithm. Okay, it's A star search algorithm. And we'll take a look at the pseudocode there. There you go. So it starts off with closed set being an empty set. Well, there you go, set theory, in application. So how do you write this algorithm in C or C++? C and C++ or even Java has no intrinsic, representation of a set. Now some people might say, but Tag, I know the standard template library, or at least that's the old name of that thing, and there's a template class called a set, right? You can make a set out of integers, you can make a set out of strings and whatnot. So, but it's not built into the programming language itself, and the implementation of the set template is really quite costly in C and C++. It's not really down to the bit level, so it's actually not very efficient. So anyway, getting back to this. Okay, cool, Tag, you just found an A star algorithm that has that makes use of the set representation or make use of set concepts. But this may be a totally useless algorithm, just so that I can show you something that makes use of set representation. What does the A star algorithm do? Why is it? Oh, okay, go ahead.
I can't remember.
Okay, go ahead.
It calculates the shortest path between 2 points on a grid.
It finds the shortest path between just two vertices. Okay, so we will get to the A star algorithm in this class at the very end of the semester. But it basically finds the shortest path. Just kind of imagine that you map out the time to drive from one point to another point. Let's say it's in San Francisco. Okay, and you can even factor in the probability of encountering a red light and how long it takes for the red light to turn green and stuff like that. Okay, and you take into consideration time of the day, blah, 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 blah. Okay, so with all that data, how can you figure out what is the quickest route from one particular place in San Francisco to another place in San Francisco, given a particular time and you already have all the statistical information with you? How do you do that? The A star algorithm. So do you think the A star algorithm has practical use?
Yeah.
It has a lot of practical use. Okay, well, the A star algorithm has certain problems that makes it not really ideal in some, actual practical application, but it forms the basis of a lot of the more practical variations of the A star algorithm. In other words, getting back to here, the understanding of what a set is, or how to represent a set in a programming language, is actually practical, it's useful. Okay? All right, so let's move on to the next one. The next one is a really, really short slide. It's just a representation of the thing. The cardinality is a fancy word of how many things are in, okay? So in this case, when you look at the set T, which is a set of the cars that I like, there are 3 elements in it. So we say the cardinality of T is 3. And then we use bar to represent cardinality. Okay, so are there any questions about the definition of cardinality? It basically just says, it's just saying how many things are in a particular set. Count. Now, but that can be a little confusing too. So let me give you a quick example, and you guys can kind of think, okay, what do you think is the answer of this? So we have a set like that, and I just want to know what is the cardinality of this entire set.
4.
Yep, 4 is the answer. Because as far as the set that we are considering is concerned, the first element is a set on its own, but we don't really care about how many things are in this particular set, because from the outer set, the perspective of the outer set, this is just one element. Okay, this set by itself is an element of the outer shell. So there's one element. This is a 2-tuple, but it's just one thing from the perspective of the outer set. This is one element. This is one element. So we have 1, 2, 3, and 4 elements. So the answer is just 4. Is that okay? Are there any questions about what counts as an element and what does not count as an element? Yep.
Does an empty set count?
An empty, well, okay, it depends on where you look at an empty set, okay? So let me give you an example here. That is easy. There's nothing inside an empty set, okay? But this is different because now we have a set that has an element that is an empty set. So it is an element. The empty set itself is an element of the outer set. So in this case, the cardinality is actually 1. Because there is one thing in this outer set, and that one thing is an empty set itself. It's kind of like a folder in a folder. Okay? So if I'm asking you how many things is in a particular folder, and it has a folder inside, you have to say there's one thing inside this outer folder. But what if that inner folder has nothing in it? Well, it doesn't change anything, because from the outer folder's perspective, you still have one item in the outer folder.
So you're looking inside of it.
Then you see there's nothing inside the inner folder, but there's still one thing inside the outer folder. It's not empty. All right. Is that okay so far? Are there any questions in terms of the concept of these things? No questions? Okay. So I think the whole class is here. I'm going to pass the roll sheet again. All right, so cardinality is done, and the Pigeonhole Principle is actually on the syllabus of this class, so I have to include the discussion of the Pigeonhole Principle. And every time I talk about the Pigeonhole Principle, I cannot help but have this image in my mind. Okay, it's a children's book called "Don't Let the Pigeon Blah Blah Blah." Okay, so don't let the pigeon run this app. Don't let the pigeon drive the bus. Don't let the pigeon sleep late. And so on and so forth. But for some reason, this image just kind of pops up in my mind every time I encounter this phrase or encounter this concept, the Pigeonhole Principle. So the Pigeonhole Principle is not exactly a part of set theory, but it can be applied that way. So the key idea here is this part here. If there are n things to put m non-intersecting sets, and n is greater than m, then at least one set AK has more than one element. Okay, that's a really awkward way of saying that if you have n distinct items, and you only have m bins or buckets or slots to put those things in, then at least one slot has more than one items. That's all it's saying. That's called the Pigeonhole Principle. Is that okay? All right. But how do we prove that the Pigeonhole Principle is, as a theorem, is true? Okay, let me just rephrase what I'm asking here. The Pigeonhole Principle is a principle, and people think it is true. Okay, in other words, most people think intuitively that if you have more distinct items than you have bins, and no matter how you put the items into the bins, at least one bin will end up with more than one items. It makes sense to us, right? Most people say, I cannot come up with a counterexample, so the theorem has to be true. Well, that's not how you prove a theorem. You cannot just say, I cannot find a counterexample. So now the question is, how do you prove that Pigeonhole Principle as a theorem, as a proposed statement, is always true? Not just sometimes, not only for the examples they can come up with, but always true. So what do you do about proving this? Well, the answer is here. For those of you who read ahead of the class, you should probably recall the concept of proof by contradiction. Okay? Now, proof by contradiction is something that we are going to encounter, or we're going to make use of multiple times in this semester, because it is a really powerful way to prove theorems. Now, you might think, it is counterintuitive. Contradiction, I thought contradiction is only good for proving something is wrong. So how can proof by contradiction be useful for proving something is true? Well, the key is to change the theorem that you want to prove first. Okay, so you invert it. Whatever it's saying, you say it's not true. Okay, and then we throw it into the rest of the system, and then we say, okay, is that going to cause problems if this theorem is assumed to be false? And in this case, it causes problems, because if the theorem is wrong, okay, that means if you have more distinct items than you have bins, there is a way to put at the most one item in each bin. That's the flip side of the original theorem. Is that okay? Because the original theorem is saying, okay, given that you have more distinct items than you have bins, then at least one bin is going to end up with more than one item. So when you turn that around and say, okay, what is the flip side of this theorem, then it's basically saying if you have more items than you have bins, then in at least one occasion you can find a way to put no more than one item per bin. So let's say that's true, right? You have no more than one item per bin. And you only have m bins, and m is less than the number of distinct items. So that means if you add up all the items in all the bins, up to how many items can you get? Only m items, right? The same number as the bins. You cannot have more than that, because you are basically assuming the theorem is wrong, and can find a case where you can put at the most one item per bin. But hold on a second here. We started off with n items, and n is greater than m. But when you collect all the items from all the bins, you can only add up to, at the most, m. And here's a contradiction, because now m is greater than or equal to n, which is contradicting the assumption of n being greater than m to begin with. Okay? If you don't follow this proof, just because I'm just saying it out loud, don't worry, we will see this again. But I guess that's why some people worry even more. It's like, Jack, are you really sure we want to touch on this again? Yes, we are going to touch on this, and we'll beat this to death, several times. Because proof by contradiction is a very, very important proof technique. So you gotta, understand that one. All right, so that is done. I opened up a quote-unquote homework assignment. This one does count for your grade, so you need to work on this individually. But it is open book, open notes. I'm not going to check whether you guys, read the notes while you're doing the homework assignment, go ahead and do that, okay? Go to Wikipedia, go to Mathematica, and check on all the definitions, okay? That's okay, that's not a problem. I do want you guys to work individually, so don't help out someone and say, oh, the answer of this question is blah, 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 okay? Because I want everybody to work on his or her own homework assignment. And this is your homework assignment is due next Monday. You have an entire week to work on it, but I would suggest that you work on it as soon as possible, because if you have problems with this homework assignment, we should probably go over some of the topics that we have already gone over. Okay, and that's the purpose of homework assignments. It's not really just an assessment for you to assess how much you understand. It's also an assessment for myself to make sure that I'm teaching the concepts sufficiently in the class. So if you guys do it as soon as possible and raise questions, I can adjust the teaching material to respond to that. All right, and the very last slide of set theory is basically just saying, okay, do we really need to understand the concept of set theory in real programming? Well, when you consider real programming, what is a real programming language from your perspective? What is a quote-unquote real programming language? I mean, there are certain languages that are not really considered real, like, oh yeah, it's a toy programming language, nobody cares about that. What do you think is a real programming language? C#. C#. Well, it's from Microsoft. See, the recorder cannot record this. I can do this all day long. Okay, well, but there are real applications of C# and people do use C#. Very good, okay? Java is a real programming language. Does anyone want to do this? Okay, go ahead.
Anything that's Turing complete, so like Lisp.
Okay, but Lisp is a really useful programming language. I like it a lot, but it's not used a lot in real life, unfortunately. Okay. What about C? Do you think C is a practical programming language? Not C++, just plain old C. No, somebody shake his head. Okay, it's like, who in the world would use C? We got Java now, okay? Why do we want to use C? Can someone name some product that is famous and it does use C for the most part? Yep.
I would say pretty much any game engine.
Any game engine, okay? But even games have to run on top of something.
Right.
Usually things that have less memory, like microcontrollers and whatnot, use C and other more memory efficient programming languages. Because C++ basically comes with everything under the kitchen sink.
And what is the basis of C++? What is it built upon?
It's built on C.
Right, yeah. Okay, but there are programs written in pure C and not C++. There's not a sprinkle of C++ in it. Yep.
The Linux kernel?
The Linux kernel, thank you. Okay, and why is the Linux kernel important? I think that's just really some self-radicalized people using that particular operating system.
Servers.
Okay, who has an Android phone? Okay, who has an account on some server?
Right.
Okay. Here's the other one. Who has a? Since I asked Android, I only feel it's fair to ask who has an iOS device. Who has an iOS device? Okay. And guess what is the operating system underneath iOS? Well, it's not C. C is a programming language. But the operating system is closely related to C. What is the underlying operating system of iOS? OS 8. BSD, very good. Okay, BSD stands for
Berkeley Standard Distribution?
Yep, and it is a variation of
Unix.
Unix, very good. Okay, Unix. Never heard of that term. Okay, I know what is iOS, I know what is an I whatever, but I have never heard of BSD. What the heck is BSD, right? Okay, what about Android? What is the underlying operating system of Android?
Delphic. Linux.
Linux, very good. Okay, and Linux is a Unix-like operating system. It is for the most part, POSIX compatible, which means it's a Unix type operating system. Okay, so we have BSD and Linux as the underlying operating systems of most of the mobile devices. If you have a Windows Phone, I am sorry. You are left out of this discussion entirely. Okay, so with those two programming languages, they are both open sourced programming languages. The licensing is a little bit different, but they're open sourced. What do you think what do you think is the majority of the source code? I would say at least 60 to 70% of the source code. What is the programming language of both of these operating systems?
C.
C, very good. Okay. See, all of these questions are very loaded. Come on, you guys.
He's leading.
I was just hoping somebody will say, but iOS is written in Objective-C, and so is BSD. No, it's not written in Objective-C. Okay, so C is an underlying, important programming language. Go ahead.
Are compilers written in C?
At least at some point, because it's a bootstrap process. Because how do you write a programming language when there's none to begin with?
Right.
Yep.
Aren't drivers written in C?
Drivers are usually written mostly in C and a portion probably in assembly language. Yep. Go ahead.
Yeah, I just wanted to clarify, like, what I meant is that I didn't mean that microcontrollers were written in C++. I meant to say, what I was saying is that microcontrollers are written in C because other languages have too much baggage, so it ends up using a lot of memory. And you also do little tricks like write ++i rather than I++ in for loops.
That part is really just a notation, but I understand your point. Very good. But getting back to this slide here, okay, most people do not know, what is the select call? I mean, we have never learned that term or learned that concept in C, in the C class, in cisp440. And an FD is a file descriptor, okay? But even though to us, these are fairly foreign concepts, file descriptor used in a select call, I mean, what the heck is that? This is, system level programming. In other words, at the very, very low level, this is how an operating system, a single thread program, can handle multiple connections. Okay, so let's say you're writing a program like Apache, okay, a web server or some kind like that, or some kind of program like that. So how do you write a program where you can handle multiple connections all at the same time, quote unquote, at the same time? So if one connection is really slow, it doesn't slow down the program serving some other connections. Okay. This is how people do it in plain C. There's no extra overhead of C++ on top of this. And yet, okay, the most important part is not what the select call does or what is a file descriptor. The concept of a set is utilized in this case. In other words, in this case, the select call allows you to specify, hey, keep an eye on this file, this file, this file, this file, and that file over there. If anything is to change with these 5 files, wake me up. Otherwise, I'm just going to go doze off and take a nap. Okay? Well, that is very important because if those 5 files are representing connections to the client, computers, somewhere else, that basically means, if any one of these 5 connections is ready to be fed additional, bytes, or if I can read additional bytes out of, these 5 connections, let me know, and I'll wake up and deal with that. Okay, so I'm not going to get too much into what is a select call. I'm just going to say it is important. And of course, C++ has a template class called set. It allows you to implement, all kinds of set operations. If you know some kind of scripting languages, such as Perl, PHP, or Python, they also have key pair, the key pair concept, where you can map a particular thing to a value, and that is closely related to the concept of a set as well. Okay, and then of course we have algorithms that also make use of the concept of a set, And in this case, I used the Dijkstra's algorithm and the A-star algorithm as examples because we are going to touch on these algorithms at the end of this semester. And these are also very important algorithms. So that's the kind of application, like, practical application of set concepts in actual programming. Okay. Are there any questions, comments about, the application of set theory in programming? Now, as far as we are concerned, we are not doing any type of programming in this class, but the vocabulary of about these set operations forms the basis of functions and relations, and mostly functions. Okay, functions are basically one step. It's built upon the concept of set theory, but it is by itself also just a foundation so that we can use it to describe other things. So we're going to start with an introduction to functions. We already know function in the context of programming, especially in C and C++. If there's a return type from a subroutine, it is called a function. Okay, and the invocation of the function can be in a place where that kind of value can exist. So that is how we understand functions. But what we'll do is to use a more mathematical point of view in this class. So when we look at a function, we can see a function as something that can take some input, and then from the input it can produce an output. Okay? The input, or the possible values that can serve as the input, is called a domain. So the domain is really a set. It's a set of all possible elements that the input can take on. And then the values of all the possible output of a function is called a codomain. In a math class, they typically refer to that as a range, but in discrete math, we use the concept or the term codomain, which is the same as a range. Okay? Basically, one is the input set, the other one is the output set, if you will. The domain is the input set, the codomain is the output set. So in this case, let me just define a funky, useless, and totally pointless function. I'm just defining, by definition, okay? F of 2 is 25, don't ask me why. F of 5 is 67, and F of 1 is 102. Don't ask me why, I'm just using this as an example, okay? And that's the entire function, okay? Function F does exactly that. What is F of 4 then? I don't need to consider it because 4 is not a possible input to this function. I can just say I'm not going to deal with it because it's not a part of the possible input of this function. So in terms of function notation, in this class I use, sorry, go ahead.
I was just noting that it's discrete, it's not continuous.
It's not continuous. What is the name, what is the title of this class?
Discrete.
Yep, discrete structure, and that's exactly why it's called discrete structure. We don't deal with continuous stuff. So in this case, we basically say that f is a function that maps a domain of exactly 3 elements, 1, 2, and 5. 4 is not in it, 3 is not in it, to a codomain, which is another set that has all the possible output values, which is 25, 67, and 102. That's just a notation. That's just a notation that we use in this class that specifies what is the name of the function. It's called f. What is the domain, or the input set, is 1, 2, and 5. And what is the set of all the possible output values? It's 25, 67, and 102. But it doesn't really tell you how it is mapped. It simply states what is the domain, what is the codomain, but it doesn't tell you how things are mapped from the domain to the codomain. You can also see notations like this one, okay, which is exactly the same way. It's just that it's easier for me to type the first one, the top one, instead of the bottom one. The bottom one requires me to use the superscript on top of an arrow, which is not really that much more, but it's going to be a lot harder for you guys to type in your homework assignment. So I like the first one a lot better, because the first one, you can just type it in just about any text editor. Okay. Are there any questions about the terms up to this point? A function that has a domain, and a codomain. Any questions about those three terms? No questions? All right. So now we want to say, okay, but how do we, indicate that f of 2 is 25, f of 5 is 67, and f of 1 is 102? This is not ordered. Remember, things inside the set is not ordered. In other words, it's just as good if I say 5, 2, 1, or 5, 1, 2, or 2, 5, 1, and so on. So there's no actual correspondence between, which value here maps to which value over here. There's absolutely no implication of that at all when you look at this representation. So the next question is, so how do we say that f of 2 is 25, f of 5 is 67, and f of 1 is 102? Well, this is where the concept of tuple comes in handy. So the function f is now actually defined as a set of 3 tuples in this case. So when you look at each tuple, it is a mapping of a single value in the domain to a single value in the codomain. So let's take a quick look here. The first item is a tuple, and inside the tuple we have 1, 102. So what that means is the function f is mapping the value 1 to 102. Just that. Okay? So I'm not going to waste time on the second one, but I also want to point out that the set representing a function is always a subset, not necessarily a proper subset, but it's always a subset of the Cartesian product between the domain, which is the input set, and the codomain, which is the output set. Is that making any sense? Okay, all right. So can someone come up with a trivial example where the function is the same as the Cartesian product between the domain and the codomain? Give me a particular function definition where the function itself, represented as a set, is exactly the same as the Cartesian product between the domain and the codomain. Yep.
The identity function.
Nope, that's not actually true.
Oh, sorry. So the identity function of one element.
Any function with one element in the domain and one element in the codomain. Okay, so that is true. So let me show you the exact example. And I'm going to define another useless, totally useless function, but it is a function after all. Okay, so I'm going to define a function where f of, I don't know, I'm not going to use 1. I'm just going to use some really oddball values here. I'm just going to say f of 23 is 61. And that's the entire definition of this totally useless, senseless function. It is a function nonetheless. So if this is the entire function, what is my domain? F is a function that maps from a domain, which is the input set. What is the only element in the input set? 23. Okay. And it maps values in the domain to the codomain. What is the only element in the codomain? 61. Oh, wow. Okay. All right. So now we look at f as a set. Okay. So as a set, it has 2 tuples, and it has 1, 2 tuple exactly to map the value 23 to 61. But that's the entire thing, because this is a totally pointless, useless function that maps one value to another value. But what is the Cartesian product that we're dealing with here? The entire domain is the set of 23, and then the entire codomain is the set of 61, which means this whole thing, the Cartesian product, is just one particular item, which is 23, 61 as a 2 tuple. So this is a trivial example where the Cartesian product of the domain and the codomain is exactly the same as the function itself. It doesn't happen very often, okay? I have to go to these extreme cases to show you that it is possible, but in most cases, the function itself is a subset of the Cartesian product of the domain and the codomain.
if the function is identical, it's still a subset, right? So
Say again?
if the function is identical, then it's still a subset, right? It's just
It is
not
still a
a-
subset. Very good. Okay, it's still a subset. Let me tell you exactly why that is the case. Okay, so we're going to use an example, and I'm not even going to bother with domains that have infinite number of elements. So I'm going to just say f of 1 is 1, f of 2 is 2, f of 3 is 3. Okay. So when people look at this and they go like, hey, maybe this will also fit the other description where the Cartesian product between the domain and the codomain is exactly the same thing as the function itself. But that is not the case. So let's take a look. F maps 1, 2, 3 to 1, 2, 3. That part works just fine, right? But when you define F as a particular set, okay, it maps 1 to 1, it maps 2 to 2, it maps 3 to 3. That is function F. Are there any questions about this way of spelling out the details of function F? It's just an alternative way to describe it compared to this one. It's just the other way to do this. But this is actually a proper subset of the Cartesian product of the domain and the codomain, because the Cartesian product of 1, 2, 3 and 1, 2, 3 is actually what? Well, I'm not going to spell out all the items because it's going to be a little bit time consuming. What is the what do you think is one of the elements of this particular Cartesian product? Okay, we got 1, 1, 1, 2, 1, 3, and then we got 2, 1, and so on. There are 9 elements in this Cartesian product. Is that making any sense? And that's why in this case, the function represented as a set of 2 tuples is a proper subset of the Cartesian product of the domain and the codomain. Even though it seems like, hey, but there is an identical function. I mean, if we're just mapping a value to itself, it is still a subset. Is that okay? Are there any questions about this slide here? Yep, go ahead.
Does it matter the notation we use if we put the proper subset or just the subset? Because one just has the equal, right? So would it matter?
Oh, you can use this if you want to, because anything that is a proper subset of is a subset of.
Oh, okay.
It's like between less than and less than equal to. If you can establish less than, then it also holds true that it has to be less than or equal to. But typically, when you already know it's a proper subset of, you just want to make it more specific. Because by introducing the extra bar, you're losing information in your statement. All right. So, if function is so easy to define, are there things that are not functions? Okay. In other words, what makes a function a function? Okay, so let's take a look at this here. Okay, so in general, blah, blah, blah. Okay, I'm just trying to find out where in this slide I talk about what is a function and what is not a function. I may not have that here. Well, it's this part here. There's an important qualification that makes f a function. In this case, x is still being defined as the domain and y is still defined as the codomain. And the requirement is summarized by this single sentence here. Each element of the domain must correspond to one and only one element in the codomain. Okay. Now, one and only one is simply saying it cannot be 0, cannot be 2, 3, 4, and so on. It has to be exactly 1. Okay. So let's see if we can define something that is not a function. I'm just going to use my document camera here to give you some examples, and you tell me whether it's a function or not. Okay. And the way I'm going to do this is to overlay the statement about what is a function. So it's just that statement here. And I'm going to put the document camera right below this so you can actually see the qualification of what makes a function with the example. Okay, so I'm going to start with a particular example. F is, it maps 1 to 1, it maps 2 to 1, maps 3 to 1 as well. Is that a function? It is a function because it still satisfies the requirement of each element of the domain. Okay, 1, 2, and 3 are all in the domain. They all map to one and only one element in the codomain. 1 is in the codomain. Nothing says they cannot map to the very same element in the codomain. Okay, so it's perfectly okay for this to be a function. So we'll say yes, it's a function. Okay, let's look at the other one. Okay, so f equals to 1, 1, 1, 2, 1, 3. Is that a function?
No.
There's only one element in the domain, which is 1. And the very same element maps to 3 different things in the codomain. It is not a function because it fails the requirement of one and only one element in the codomain. In this case, there are 3 elements in the codomain. Okay, let's move on to some more confusing examples. So with these more confusing examples, I'm going to be more explicit to tell you what is the domain and what is the codomain. Okay, so in this case, I have 1, 2, 3 as the domain, and I have 1, 2, 3 as the codomain. So this is given. Okay, I'm telling you what is the domain and what is the codomain, and I'm going to define f as 1, 1, 2, 1. And 3, 1. Okay, is f a function? In other words, am I mapping each element of the domain to exactly one and only one element in the codomain? It still meets that requirement. But what about the 2 and the 3 in the codomain? Nobody likes them. It's not. They're not mapped. Okay. Well, is that a requirement to be a function? Nope. As long as it is in the codomain, it is fine. Okay, so let's keep this assumption here, and this time we look at f being 1, 4, and 2, 2, and 3, 3. Okay, there we go. Is that a function? Given what is the domain and what is the codomain, is this a function? It is not a function because 4 is not even in the codomain. It's not a function. This is no good. Is that okay so far? Okay. What about this? Keeping the same assumption of what is the domain and what is the codomain, let's look at this one. Is that a function? Whoops. Let me scroll up a little bit here. There we go. Is that still a function? It is not a function. What is it failing? It's failing each element. Okay? What is failing is this part here. Now, the only thing that is listed here is mapping to one and only one element in the codomain, but it's failing this requirement, each element of the domain. Because yes, one of the elements of the domain is meeting the requirement, the rest of the requirement. What about the other 2? What about 2, which is an element of the domain? What is it mapped to? Nothing. And that's why it fails to meet the requirement of becoming a function. Is that okay? So that one statement, okay, each element of the domain must correspond to one and only one element in the codomain, is actually kind of tricky because there are several ways to fail to meet that requirement. Are we doing okay so far? Okay, excellent. So let me just throw something out again to see if you guys would consider these as functions or not. And I know it's not required, okay, because there's no such requirement for this class. Is the sine function a function?
Yes.
It's a function because it maps any value, okay, any type of degree in angular measurement to a particular value. What about arc sine? Arc sine is a function or not a function? Well, it all depends. It depends on how you define the range and most importantly the codomain in this case.
Yeah.
Okay, so let's look at all angles in radians. Okay, in radians is pi. 2 pi is one full revolution or one full rotation. So if I define sine as a function that maps, I'm just going to use this notation here to say inclusive. So it's going to, I want to be exclusive on one side and inclusive on the other side. Sine can, take it back. Okay, sine can deal with -1 all the way to 1, and these are real values. And I'm saying it maps to, I have to be careful here. Okay, so let's try this one here. Okay, I'm just mapping all the possible values between -1 and 1 to the set of all real numbers. Okay, so is this a function or not?
Yeah, it is.
It is not a function, okay? Because it has to do with the nature of rotation, okay? Because, okay, let's take a look at this picture
You
here.
have a domain point to multiple.
Okay, give me angles in radians that can give me a sine value of 0, because that's the definition of arc sine, right?
pi/2.
Okay.
0.
Okay, 0 is 1. Okay, very good. Okay.
Yeah, 0.
And then what about
Pi.
how about pi itself?
5. And 5.
2 pi, 3 pi, and so on. Oh, wait, hold on a second here. That's not a function anymore. Because a particular element of the domain, in this case 0, is corresponding to an infinite number of elements in the codomain. And that has to do with how I choose the codomain. Now, how do I fix this problem? Well, to fix this problem, I can just say, wait, let's not look at all the real numbers, okay? I'm just going to limit myself to certain real numbers. So this is where it is important to be careful, to be open on one side, and close on the other side. Let's see, would that work? Sine is, no, that won't work, would it? Okay, my trig is bad. Okay, so you're basically looking at 0 here, and sine is the height of the triangle, not the base, right? Because that's cosine. So we are looking at, this is actually pi divided by 2, and this is negative pi divided by 2, so I have to change that.
Divide by 2.
Sorry?
Just divide by 2.
Yeah. But then it can be inclusive because you have negative pi divided by 2 to pi over 2. And there we go.
Are you graphing on the polar coordinate? Are you graphing on the polar coordinate? Is that what you're thinking?
Not the polar, the radius is not important. It's really just the angle. Yep. All right. So are there any questions about this? No questions? All right. So if there are no questions about the definition, let's take a look at this obscure thing over here. A slightly clumsy, okay, with an emphasis on slightly, way to say this is for any element x, lowercase x of uppercase x, which is basically saying any element of the domain, this has to hold true. Okay, what is that? I mean, this is using some of the notations that we have just introduced today. So we'll start from the inside and then work our way to the outside. Okay? So the inside is basically for any element inside this particular set, it is in the form of a two tuple, which has two elements inside. But there's one extra requirement of this two tuple. X, Y has to be an element of F. Okay? So for any type of element of X, it has to, the cardinality of the corresponding set in F has to be exactly 1. So that's one way to say that for each element of the domain, it must correspond to one element in the codomain. Now this is actually not entirely true because I'm not enforcing that Y has to be in the codomain. But because XY itself is an element of F, that implies that Y is in the codomain. Is that okay or not?
So that's a fancy way of saying there's one.
It's a fancy way to say what we said earlier. Well, let's take a look. Okay, so we'll pop this up, and the best thing of using a document camera and a piece of paper is I can do this. I can flip back to a previous page. Okay, so let's take a look at the first example where we map 1, 1, where we have the mappings 1, 1, 2, 1, 3, 1. Does it meet that requirement? Because now we have changed the way we describe it. For each element, for any element x of x, okay, in this case 1, 2, and 3, the cardinality of all the tuples that starts with x inside F has to be exactly 1. Is that holding true? Okay, let's take a look. Let's start with 1, 1 here. Okay, this 1 is an element in the domain, cool. And there's only exactly one element in F that starts with 1 or has 1 as the first item of a two tuple. So it does meet this requirement of the cardinality of that set is exactly 1. Okay, that works out. Let's check out all the other elements of the domain. 2, 1, okay? 2, 1 is in F, meets that requirement. The cardinality of this set is exactly 1, fine, no problem. And 3, 1 is the same way. So this is a function. Let's look at the one that is not a function and see why it is not a function. So this in the second example, this is the one where it is not a function. And let's see, using this new way of looking at functions, why it is going to fail that, okay? So for any element x of x of the domain, in this case 1, let's check out whether this requirement is holding true or not. How many tuples inside F starts with 1? There are 3 tuples, right? So the cardinality of the set of all the tuples that starts with 1 is actually 3. 3 is not 1, it fails that requirement. Is that okay? Let's look at another one that fails the requirement. And that one is down here. Okay, I'm gonna scroll my paper. So we are starting with this assumption that defines what is the domain and what is the codomain, and this is the one that we want to consider. So we want to say, okay, if F maps 1 to 1 and only that, okay, but the domain and the codomain is defined with the earlier item, which is over here, is it meeting the requirement using this new way of defining what a function really should be? Well, let's check. For any element x of the domain, this has to be true. Well, let's see how many elements are in the domain in this case. We got 1, 2, and 3 elements in the domain. If you look at 1, yes, that requirement is met, because in the definition of F, 1, 1 is the only one that is in F, and so the cardinality of all the tuples inside F that starts with 1 is exactly 1. Not a problem. What about the other elements in the domain? Well, let's take a look at the element 2 in the domain. Element 2 in the domain has no 2 tuples corresponding to it in F, which means when you look at this set here, which is basically asking what 2 tuples in F starts with the value of 2, it is an empty set. What is the cardinality of an empty set?
0.
0, because an empty set has nothing in it, right? So when you ask the question, how many things are in an empty set? It is 0. 0 equals to 1 is false. And as a result, this particular definition of f fails to meet the requirement of becoming a function. Is that okay or not? Okay, all right. So I just want to give you the alternative ways of looking at things and defining what a function is. The next slide talks about predicate logic, which is a little bit out of order, but it is a very important part of our language to express stuff. Okay, so we start to introduce the concept of every and some. Okay, when you use the word every and you use the word some just as a in natural language, what is the difference between those two? What is implied when you say every?
All. That there is not one where it's not the case.
Okay, very good. Okay, I like that way of looking at it. When you say some, what is it implying?
At least one.
Some, yeah, at least one is a good definition. Okay, so at least one is some, and every is kind of like all, right? Okay, so that's a very important concept. In mathematical symbols, there's a for all, and the symbol to represent that is kind of like a upside down A, and every is known as there exists, and the mathematical symbol is like an uppercase E, but it's flipped horizontal. Okay, so it's left, right, reversed. So the word predicate, the term predicate, refers to some kind of evaluation that has a Boolean result. In other words, it's some kind of evaluation that is either true or false. Okay, doesn't have to be true all the time. Can be false. I can give you some, funny, predicates. Tak is wearing a black T-shirt. Okay, it's a predicate. It's not an assertion. It is just an evaluation of, okay, is it true or is it false at this point? Today, it is true. I would say maybe 80% of the time it's true. Is that okay? So that's a predicate. It can be an expression. In other words, x is less than y is an expression. It can be a predicate. It is seen as a predicate because it can be either true or false. In this case, x mod y equals to 0 is a predicate because it applies to any element x and element of y from the set of integers, except when y equals to 0, then it's not defined. So with that said, we can now redefine the qualifications of what a function is, but using the for all and the there exist symbols. So in this case, we are saying that x is the domain of the function, and y is the codomain of the function, which is consistent with the previous slide. First of all, f as a set has got to be a subset of x cross y because we talked about that. The importance of this is it has to be a subset, because if it's not a subset, then we have problems, because we can now have elements that are outside of what we know as the domain and the codomain. So this is the part that is really kind of important. Okay, let's take a look at what this is saying. So I'll spell it out first in English, and then we'll talk about what it means. We have about 5 minutes, that should be enough. This is basically saying for all, or for those of you who do not like the word for all, just say every, okay, because it means exactly the same thing. So it says, okay, consider all possible values, and let's call the value that we're considering lowercase x. That's all it's saying. And now it's saying x is an element of x. Okay. In other words, if you want to, you can say, oh, we know about 1, 2, and 3. What about Miata? Can I say lowercase x is Miata? Sure, throw that in. It's not a problem. What? It's not a problem? How can it not be a problem? Because if x is not an element of the domain that we are considering, the negation of that is true to begin with, and this is a disjunction, And if you have at least one side of a disjunction or the or being true, then the whole thing is true anyway. In other words, you can throw stuff, you can basically say x can assume a value that is not even in the domain that we're considering, and that statement is automatically true for those particular values. Is that okay? That's what the first part is for. That's what this part is for. It's kind of a filter. It's basically saying, ignore everything that is not in X. We don't really care about that stuff. Okay? What about X is in the domain? Well, then we better pay attention to the second part, because if X is in fact an element of the domain that we are considering, the negation of this element of is going to be false. If one side of a disjunction is false, well, we better look at the other side. So that means this part here is applicable only if X is an element of the domain that we're considering. If X is not an element of the domain that we're considering, hey, all this stuff is going to be true anyway. Is that okay? So this part, the part that I have just highlighted, is exactly the same as what we talked about in the previous slide, but in this case, the only addition is the concept of for all, and also the concept of filtering, and just say we're only paying attention to stuff that is in X. For everything else is automatically true. Don't bother with that. Is that okay? And I think we're running out of time because that clock is actually slow. So we'll continue this on Wednesday, but I need you guys to read at least up to this point and possibly 1 or 2 links in Moodle ahead of me. Okay, because this stuff is starting to get a little thick. So if you're not familiar with the terms, then it gets really hard to understand the stuff in the class.
Listen, I don't understand how